Let's move on now and talk about advanced conversions. One thing that you need to keep in mind when we talk about advanced conversions is the fact that we're moving past the idea of a one-step conversion, like going mole to mole or mole to gram or gram to mole. Now we're going to be doing upwards to 2 or 3-step conversions. So it's really important here for you to remember that you need to label and stay organized. Let's see what this looks like. Translate the chemical word equation to a formula equation. Aluminum metal combines with oxygen gas to produce aluminum oxide, and we see a sample of aluminum oxide up here. So aluminum metal we're going to represent as Al. Combines with is our plus sign. Oxygen is O2. To produce, arrow, and aluminum oxide. And remember, aluminum is Al plus 3. Oxide is oxygen as part of a compound, minus 2. The 3 is going to cross down. The 2 is going to cross down over there. So we're going to get Al2O3. The next thing that we need to do is to balance it. We could start with the aluminum, but I would hesitate doing that because I see 2 oxygens here, 3 oxygens here. I know I need to balance them. So I'm going to put a 3 here to get 6. I'm going to put a 2 here to get 6 oxygens. I have 2 times 2, that's 4 aluminum. I'm going to put a 4 over here, and that will give me my balanced equation. Now I want to move on and look at what the question is asking. What is the minimum number of grams, so mass, of solid aluminum required to produce 74 grams of aluminum oxide? So here my given is 74 grams of aluminum oxide. So I'm going to write that down first. 74 grams of Al2O3. Now, I need to ultimately get to grams of solid aluminum, but I can't just go from grams of aluminum oxide to grams of aluminum. So what I need to do is follow the AP Chemistry mantra and convert to moles. So if I start with grams of Al2O3, that's going to go on the bottom. Grams Al2O3, and I know that is equal to 1 mole of Al2O3. And the gram formula mass of Al2O3 is roughly 102 grams. Now I need to get from moles of Al2O3 into moles of aluminum. I'm always going to do this middle step here if I need to get from one substance to another. So moles of Al2O3 getting over to moles of just Al. And just like a mole-to-mole problem, I'm going to look back at my coefficients from my balanced equation, and I'm going to see that I'm going to have a 4 on top, matching this 4 right here, and a 2 on the bottom, matching this 2 right here. So now I'm out of Al2O3 and I'm into moles of aluminum, but I don't want moles of aluminum, I want grams of solid aluminum. So the last step here will be to get from 1 mole of Al and get to the mass of Al. So 27 grams of Al. Do I have this set up? I can check that by saying to myself, grams of Al2O3 cancels grams of Al2O3. Moles of Al2O3 cancels moles of Al2O3. Moles of aluminum cancels moles of aluminum. And I'm left with grams of aluminum, which is what I want at the end here. And if I do all the math and I do it correctly, I should get around 39 grams of aluminum, which is what I want at the end. Plus, that also matches up to the number of significant figures that I started with, which 2 significant figures right here. So I need 2 significant figures at the end. Now let's look at an advanced conversion. In other words, we're going to use Avogadro's number when we do this particular conversion. Given the reaction, ammonia is combined with oxygen to produce nitrogen monoxide and water. So the first thing that we're starting with is ammonia. And we know that ammonia is NH3, is combined with, that's a plus sign, oxygen, which is O2, to produce, arrow, nitrogen monoxide. NO, and water, plus H2O. What is the maximum number of molecules of nitrogen monoxide that can be produced when 3.2 times 10 to the 22nd molecules of ammonia are completely reacted? Okay, so the key words here are the use of the word molecules. Okay, so we're using molecules. Whenever you see the word atom, ion, molecules, formula units, and we're doing a conversion like this, you know that we're going to have to use 6.02 times 10 to the 23rd somewhere in our setup. Because really what we're going to be doing here is taking this number, this 3.2 times 10 to the 22nd, and converting it to moles. Then we'll look at the next step. So I'm going to write down my given. 3.2 times 10 to the 22nd molecules of ammonia, NH3, multiplication sign, and a line. Okay, so if I'm starting with molecules, that means my molecules are going to go on the bottom. And if I'm labeling something as molecules, I'm going to do 6.02 times 10 to the 23rd molecules. Always will equal 1 mole. In this case, we're talking about 1 mole of ammonia. So now I'm in moles of ammonia, but I don't want to be in moles of ammonia. I need to actually get to molecules of nitrogen monoxide. So this next step is going to be going from moles of ammonia to moles of nitrogen monoxide. So this middle step here commonly will be a mole-to-mole problem. So I'm going to put moles of ammonia on the bottom, because just like before, whatever I start with has to go on the bottom. I want moles of nitrogen monoxide, and then I go back up to my balanced equation here, which I forgot to balance. So hey, let's do that right now. All right, NH3, O2, NO, H2O. I look at this and I say, all right, one nitrogen, that's good. The oxygens are definitely not balanced, but it's these hydrogens that I'm thinking are looking a little strange. So initially what I want to do is say to myself, all right, let's balance the hydrogens and see what happens. So what if I put a 2 here and a 3 here? A 2 here and a 3 here. So that will, oh no, wait a second, we can't do that. Because even though I've got 6 hydrogens right here and 6 hydrogens right here, I automatically have 2 nitrogens here. I need to get 2 nitrogens over here. But I'm looking at this and I'm saying, ultimately, if I put a 2 here, I'm going to get an odd number of oxygens. And I don't want an odd number of oxygens. So what I have to do is stop, erase, and start over. So instead of putting a 2 here, I'm going to double that 2 and make it a 4. Because that should help me get rid of my odd number of oxygens over here. Just that's one small little step. So now I'm going to have 4 times 3, that's 12 hydrogens. I have 2 hydrogens right here, which means I need to put a 6 in front of here. Now let's see how that has affected my nitrogens. Well, now I have 4 nitrogens here. I need to have 4 nitrogens here. But what does that do to my oxygens? Well, 4 oxygens here, 4, 6 oxygens here. We know 4 plus 6 will give me a 10, which means there needs to be a 5 in front of the O2. All right, so we finally have our balanced equation, which we should have done first, but oh well, we fixed it. We recognized that we had to do this. How does that affect this middle part right here? Well, the number of moles of NH3 is 4, so we're going to have a 4 on the bottom. And the number of moles of NO is also going to be 4. Interesting. So ultimately, those will end up canceling each other out. That's okay. But what do we do next? All right, now we're in moles of NO. So moles of NO is going to go on the bottom. Moles of NO. And we also want to get to molecules of nitrogen monoxide. So 1 mole of NO is equal to 6.02 times 10 to the 23rd molecules. And I'm going to run out of room, so I'm not going to write it, but we're going to say, hey, look, that's molecules. And then we're going to solve for our answer, which turns out to be sort of interesting if you look at it for this reason. I know that molecules is going to cancel molecules, moles cancel moles, moles of NO cancel moles of NO. But then something else interesting comes up. You could enter all these numbers into your graphing calculator and get an answer. But I also recognize that this 4 and this 4 cancel each other. That this 6.02 times 10 to the 23rd cancels this 6.02 times 10 to the 23rd. So guess what our answer is after all this work? That's right, people. It's the same answer that we started with. 3.2 times 10 to the 22nd molecules of NO. In the grand scheme of things, you might have recognized this from the very beginning, but no matter what, you need to show some work to demonstrate your understanding. So really, it's okay that you wrote all this. Let's look at our next reaction. 2KClO3 decomposes into KCl plus 3O2. So instead of having you write the chemical reaction and giving you words, I'm just giving you the chemical reaction to start with. What is the total number of grams of KClO3 needed to produce 120 grams of O2? All right, what is our given? Our given is 120 period, which means I have 3 significant figures here, grams of O2, multiplication sign, and a line. What I want to do here, of course, is to convert to moles. The age-old mantra, convert to moles, convert to moles. So 1 mole of O2 is equal to 32 grams of O2. All right, now I'm in moles of O2, but I don't want moles of O2. Ultimately, I want KClO3. So this middle step, yet again, will be a mole-to-mole problem. So moles of O2 to moles of KClO3, that's a K. And then I look up at my balanced equation. The number in front of the KClO3 is 2. The number in front of the O2 is 3. And now I'm in moles of KClO3. But I don't want moles of KClO3. They specifically ask for grams, which is mass. So 1 mole of KClO3 has a gram formula mass of 123 grams of KClO3. And then yet again, I'm going to double check to make sure that I have this set up correctly before I do all of the work of the math. So grams cancel grams, moles of O2, moles of O2, moles of KClO3, moles of KClO3, and I'm left with grams of KClO3. So if I work this out for my final answer, if I plugged it into my calculator, it's around 307.5 grams, but I want 3 significant figures, which means I need to round this up to 308 grams of KClO3 is my final answer. Here it is so incredibly important to label and be organized when you do this type of problem. All right, the next one. Sodium hydroxide reacts with sulfuric acid to produce sodium sulfate in water. Sodium hydroxide. We know that sodium is Na plus 1. Hydroxide is OH minus 1. Sulfuric acid. You should know that acid. So when I write this formula out, this is going to be NaOH. Sulfuric acid is H2SO4 to produce sodium sulfate. Now sodium is Na plus 1. Sulfate is SO4 minus 2. So I'm going to cross this down to here. I'm going to cross this down here. But as we've said many times, no positives, no negatives, no ones. So this formula is going to be Na2SO4 and water plus H2O. All right, now let's balance this thing. If I was going to balance this, I'd start with my NAs. I have 1 Na here, I have 2 here, so I'm going to put a 2 in front of that. So the NAs and NAs are balanced. Then I'm going to look at the sulfurs because I'm going to leave my hydrogens and oxygens to the end. So 1 sulfur, 1 sulfur. I think I'm going to look at it's sort of a toss-up here. I think I'm going to look at my hydrogens next. So I have 2 hydrogens here plus 2 hydrogens over here. That's a total of 4. So to get a total of 4 hydrogens on the product side, I'm going to put a 2 in front of here to give me 4. So 2 hydrogens plus 2 hydrogens gives me 4 hydrogens. And now I'm going to hope a lot that my oxygens are balanced. So on the product side, I have 4 oxygens here, plus this 2 distributes through, so a total of 6 oxygens on this side. And how many do I have over here? I have 4 oxygens right here, plus the 2 that are right here, so I'm balanced. I have a balanced equation. I'm good to go. What is the total number of formula units? Oh, there's that word. Formula units of sodium hydroxide needed to react completely with 125 grams of sulfuric acid. Now remember, if you see the words atoms, ions, molecules, or formula units, you are going to have to use 6.02 times 10 to the 23rd. So we're looking for the total number of formula units, but we're starting with 125 grams of sulfuric acid. So we're always going to start out with our given, 125 grams of H2SO4. Multiplication sign and a line. Grams of H2SO4 will be on the bottom, and 1 mole of H2SO4 will be on the top, because we know that we want to get rid of grams and convert to moles. Our first step will always be converting to moles. What is the gram formula of sulfuric acid? Well, that would be 98. So now I'm in moles of sulfuric acid. I need to get into moles of sodium hydroxide. So I'm going to get moles of sulfuric acid, H2SO4 on the bottom, moles of sodium hydroxide up on top, and then I'm going to look at my balanced equation. So the coefficient in front of the sodium hydroxide is 2. The coefficient in front of the H2SO4 is 1. And now I'm in moles of sodium hydroxide, but I can't stop there. I need to get to the total number of formula units of sodium hydroxide. So I have 1 step left. So a multiplication sign and a line. I'm starting with moles of NaOH. That means I'm going to put 1 mole on the bottom, because 1 mole of anything, like NaOH, is equal to 6.02 times 10 to the 23rd formula units of sodium hydroxide. So yet again, I take a moment and I make sure that I have this balanced correctly. Grams of sulfuric acid cancels grams of sulfuric acid. Moles of sulfuric acid cancels moles of sulfuric acid. Moles of sodium hydroxide cancels moles of sodium hydroxide. And I am left with formula units of sodium hydroxide. So if I work this out for an answer, I get 1.54 times 10 to the 24th formula units of NaOH as my answer. So 1.54 times 10 to the 24th. That should be a 4 there. Formula units of NaOH is my final answer. Also making sure that my significant figures that I end with matches the significant figures that I started with. Last problem. Given the reaction, methane burns in air to produce carbon dioxide and water. Looks like a combustion reaction to me. Remember, there's a certain amount of organic chemistry that you must remember, and methane is CH4. Burns in air, that means diatomic oxygen, O2, to produce, arrow, carbon dioxide, that's going to be CO2, and water, plus H2O. And then I'm going to balance this. When balancing any type of combustion reaction, always start with the carbons. So 1 carbon, 1 carbon. Then go to the hydrogens. 4 hydrogens, I'm going to put a 2 in front of here to make 4 hydrogens. Finally, at the end, I consider the oxygen. I have 2 oxygens on my product side plus another 2 oxygens to give me a 4. That means I'm going to put a 2 in front of the diatomic oxygen to give me 4 over on that side. So let's look at this equation at the end. What mass of oxygen is needed to completely react with 1 mole of methane? This is an interesting type of problem because we're not starting with mass or formula units, atoms, molecules, whatever. We're actually starting with 1 mole of a substance, and that is our given. So 1 mole of methane, which is CH4, multiplication sign and a line. If I start with moles of methane will go on the bottom. And I want mass of oxygen, but I know I can't go directly there. I need to go to moles of oxygen. So we're starting out actually with a mole to mole problem. So moles of methane on the bottom, moles of oxygen. I look at my coefficients. There's a 2 in front of the O2. There's an assumed 1 in front of there, so I'm going to put a 1 there. Multiplication sign and a line because I'm in moles of O2, but I don't want to stay in moles of O2. I want to get to mass of oxygen. So I know that 1 mole of O2 is equal to the gram formula mass, which is 32 grams of O2. And I want to make sure that everything cancels. So moles of CH4, moles of CH4, moles of O2, moles of O2, and we're left with grams of O2, which is what we want our final unit to be. So if I do 1 times 2 times 32 divided by technically 1, I'm going to get 64 grams of O2. Now you might say, well, you only started with 1 significant figure, so what should your answer really be? It should be, if we're really concerned about significant figures, it should be 60 grams of O2 for our correct final answer considering significant figures.